I am unable to get rid of this. There we go. All right. So sometimes it's harder to figure out what that looks like when you have two things that you are indexing at the same time. So your key values are two things, right? A and B. So that means at the leaf level, you're going to store the A value and the B value plus a pointer to the tuple. So I'm not going to basically draw individuals, but imagine that there's a pointer to the tuple, pointer to the sibling node. For each of these, there's a pointer to the tuple, and pointer to the next node, and pointer to the tuple like this. And the upper nodes point again the same way. So basically, you need to write a decision point between these two. So now it indexes two things but doesn't have duplicate values. So it's exactly like the one we have seen. So what is the decision point between these two? What's the smallest value here? 1, 5. Okay. So now your key value is a pair, but the rest is the same. The point between these two is 3, 2. Okay. 6, 1, and 8, 1. And the decision point between these two trees is, this left tree and the right tree is 5, 8. Okay? So logically, there is nothing has changed, right? So this is our prototype index on A and B, two attributes. But it will be the same if your index was on, instead of integers, it could be strings, right? The strings are sorted lexicographically. It could be year and title. It could be any combination of attributes. It could be 2 attributes. It could be 3 attributes. So the more attributes you stuff here, the fewer things you can put, so your n will get smaller, right? So if you are indexing multiple things, your index is larger because each index node can store fewer things. And it is likely deeper because you will need more and more of those to index them. Now let's see what happens for these different searches. So if I'm searching for A is equal to 5, what do? I basically do the same thing that I was just doing. Now A is equal to 5, this is 5, 8. So that means values with 5 but some other B may be to the left of here, but probably to the right of this node. So if any value with 5 is there, I will start from this node, and I will start scanning until I find a node that has a value greater than 5, right? So this is like a range search. It's basically range of all B's, right? So A is equal to 5, but for all B's. So A is equal to 5 means regardless of B. I'm going to say B, I don't care. Right. What if I search for A is equal to 5 and B is equal to 9? Okay. This is exactly as what I was doing before for equality, because this is actually the same thing as just having an index on A and searching for A is equal to 5. So now I'm searching for 5, 9. 5, 9 should be to the right of this, and 5, 9 should be to the left of this. So if 5, 9 exists, it must be in this node. And if it is there, I can find the tuple ID. If it is not there, then I fail, right? So basically, the nice thing about the index is that if I don't find the tuple, I know that it does not exist, which is very nice, right? So this search is very much like the other search. What about A is equal to 1 and B is between 2 and 5? Okay. This is running into some small issues. So now A is equal to 1 and b is between 2 and 5, I'm going to treat that a little differently. First, I'm going to start with a is equal to 1 and b is greater than or equal to 2. So I'm going to first search for this value, find the first node that satisfies this condition. So it's going to be to the left of here and to the left of here. So start from this node, and then start scanning these nodes from here left until I find a value that is outside of this range. So this is similar to what I had, except I'm going to pick the starting point, and then I'm going to start scanning from a is equal to 1 and b is the first value where b is greater than or equal to 2 and less than or equal to 5, and then scan the sibling nodes until I find a node that is outside of the range, right? So this is basically a range like the other ones. So let's write some of these down, and then we'll see other versions, right? So this one, same as searching a is equal to x for index on a, right? So this is equality search is very similar to equality search. If you have two things, the equality search of two things is equal to equality search of one thing. If I have this one, what I want to do is search for a is equal to x, search for first value with and then scan leaf nodes to the right following sibling nodes. Okay. And what was the other one? It was a is equal to x, no b value. This is very similar to the other one. Search for first value with a equals x, regardless of b, right? So we don't care about b. Scan leaf nodes to the right, following sibling nodes. Okay. How about this one? How about now I'm searching for a is between x1 and x2 and b is equal to y. But let's go back to our example. This is a very good question. Okay, can I search for the y value? Right. So this is like saying, find a is. This is like saying a is between 1 and 5, and b is equal to or 1 and 6, and b is equal to 2. Right. How do I search for b is equal to 2? Right. So like the y. There is a b is equal to 2 here, b is equal to 2 here, b is equal to 2 here, right? But nothing on top tells me where they are, right? So indeed, the b condition is actually not very useful, but I cannot disregard it. So I can scan for a. I can scan for a between 1 and 6. Start from here and scan until I see a b value that is not 6, right? But for each one I find, I only need to find the values where b is equal to 2, right? But I still actually have to scan the index. This is like similar to what earlier was asking, right? So we have to scan the index, right? So technically it is there, but there is no search index. The search structure doesn't help me, right? So so basically this is the example where I need to search only for this, Then I'm going to scan leaf nodes for this, following sibling nodes. Then, for the nodes that I find, check if b is equal to y, and if so, put in the output. Okay. And I've actually ordered these in the kind of order of usefulness, right? So if you're indexing on two things, it is made for this sort exactly. So this is the most efficient thing you can do. This is the second most efficient thing you can do, right? This is kind of less efficient because there are many b values, but that's okay. That could be a useful thing if you actually want to use the index to find the b values for that a. But if you were only interested in a's, it is irrelevant that you have the b values, right? It's only making your index bigger. So this is not useful if you have no interest in b's. If you do, it is very useful. This is even less useful because you have this b's value, but it's actually not allowing you to search for it, right? It would have been much better if my index was reversed. How would it be reversed? Right, ordered by b first and a second, right? If it was an index on b than a, then this would be more efficient, like this one, right? But if it's ordered on a and b, this is not as efficient, right? So it's important how the index is ordered. It's useful for this one and not useful for that one. And what is the least useful search query you have? Give me something that is less useful than this one for this index. B equals y, right? So that's even worse, right? What about if I have b equals y, right? No a condition whatsoever. Okay? So then what you can do is find the first leaf node, scan all leaf nodes following sibling nodes. For each tuple, if b is equal to y, add to the output. I mean, technically, you can also have a range on b. B is between y1 and y2, right? Now, the point that I would like to make here is that this, even though the index is less useful, it may still be much better than actually scanning the index if there are only a few tuples that have this value, and the index is much smaller at the leaf node than the rest. Okay? So remember we said that the leaf node is likely stored consecutively on disk, so scanning the leaf node may actually not be so bad. And if it really helps you with the rest of your query, this may actually really speed things up. This is actually a well-known thing. They call this kind of thing index scan or index-only scanning. Even though you are able to, you are doing a big scan that may be useful for some queries. So this is not like totally useless. And the reason people like B-trees is because they are so versatile, right? All of these are possible. So because of that, B-trees have so many uses, so we like to use them. You can use a single index, and you can use a single attribute, multiple attributes, but the ordering matters, right? So if I create an index on, for example, index on actor ID, so let's say movie roles, actor ID, movie ID, right? So the index that I give you is going to be on movie ID, actor ID. So you will see both. So if I have an index on actor ID and movie ID, this index is useful for finding what kind of queries, for example. Do you ever go to Internet Movie Database? So there are two basic pages. There's one page where you go to a movie and find all the actors in that movie. And there's another page, you go to a actor page and then see all the movies for that actor, right? Okay, so which one is better for, which one this one helps? Right. Given an actor, finding all the movies is easy because it's actor equal to something, and then all the movies are at the leaf level, right? But it's not very useful giving in a movie, find all the actors. What would happen if you want to actually be able to do that one very fast also? Well, you create a second index. You create one for the second version. So you can create one index on this. Call that I1. Then you will create one on this. Okay. And they are called secondary because you can have more than one, right? However, your data is stored, you can have multiple indices on the same thing, and now you can do this. But of course, there is a trade-off to creating many indices, because every time you actually add new tuples, you also have to update these indices. So, there is a cost to maintaining these indices. So if your data doesn't change very often, then create many indices. If it changes very, very rarely, then create indices, any index that you can think possibly, right? Because maybe at night you add 5 movies, but that's not really the main traffic of your site. We will talk about that when we talk about tuning. Okay, so any questions on search? This is the main thing you have to do for your homework. Now, generally speaking, when I look at operations like this, the thing that I care most about is how many disk pages do I have to read to really answer this question, right? So, because really reading a disk page is very costly, and as a result, that's the main unit. How many disk pages I have to read to answer this. But we learned that if your data is stored on magnetic disk, it matters that data is stored consecutively, how many scans you have. But like for the homework, I don't care. In real life, you might care. So that will also be an important part of this. And in fact, in real life, you will also find out that the root is always available in memory because you always use the root of the index. So you never actually read it from disk because it's almost always cached. But things like that. We will talk more about that. All right, so let's talk about insertion and deletion. Okay. So when you are inserting a new entry, okay, so let's say you want to insert 55. So the first thing you will do is you will actually search for that value and find where 55 would be if it was actually in the index, right? So first search and find the leaf node for 55. If this leaf node has space, then you can simply add it there, right? So in that case, there's nothing to do. So in this case, if I had this node, so I had 53, 54, and 63. So if I'm bringing 55, I'm going to put 55 here and 63 here because there is space. And then you look and see if the node above needs to be updated. In this case, it will not need to be updated, right? So if there is space, insert into the node. So that's the first step of insertion. So find leaf node to insert the new value. If there's space in the new node, in the leaf node, insert. Okay. So that's very easy because since you search the other nodes to get there, your search criteria in the other nodes is already valid, right? So you don't need to change anything. Now, if the leaf node is full, remember capacity of n. If the leaf node is full after you insert, okay, everything I write looks like Python. Okay, so otherwise, I am going to create a new leaf node, right? So create a new leaf node. So that means I'm going to have to store a new disk page and distribute entries for the node, for the new node, for the leaf node to the two nodes evenly. Okay, so so basically, if it was 4, now I have 5 things. So there will be 2 and 3. I don't care. So you put 3 in one and 2 in the other, or 2 here and 3 other. Doesn't matter. Okay. So, and then of course now you have a new leaf node. Then you're going to insert the pointer to that node recursively in the parent node. So recursively insert a pointer to the new node in the parent node. Okay. So so let me draw this that was leading to this. So I had 66 and 78. Okay. So I was able to insert 55, which was fine, coming up to this node. But now suppose I need to insert 56. 56 is not going to fit in here. So this node still exists. This is an old node. So now I'm going to insert 56, but 56 doesn't work. So I'm going to create a whole new leaf node. So this was pointing to here, but I'm going to actually insert the whole new node here. So this one is now going to point here. This one is going to point here. And I'm going to distribute these 5 values, 53, 54, 55, 56, and 63, among these 2. So just for simplicity, I'm going to put these 2 here, 56 and 63. And now I need the pointer to this node, so I can search from the upper node. So the same exact logic applies. If there's a space here, right? Remember that I can have at most 5 pointers here. So if there's space here, I can directly insert it here. So I'm going to insert, so I'm going to move this, shift this here, make this pointer here. I'm going to put, this was 78, and I'm going to put 66 here. And then I'm going to put the division between these 2, which is 56 right here. Okay. So basically, I have found the right place for the 56, and then I adjusted and added the pointer for that. And now I am done. If for some reason when I'm doing this, the internal node also doesn't have enough space, right? So if at some point I need to insert a pointer, but this one actually has, let's say, 1, 2, 3, 4, 5 pointers. In that case, I'm going to split that node into 2, distribute the pointers, and then insert a node to the parent node. Okay. So you go until you are done. So if you were to write this algorithm, if the parent is full, this is not a great algorithm, but there will be better one, then split the parent, distribute pointers and key values evenly, and recursively. It doesn't help if you say recursively, but recursively insert to parent. Now, if you actually write this for good, this algorithm doesn't work because it actually is kind of, eventually it has to become self-aware. So this will not work. So what you will generally do is, we will call this insertion helper, okay? And then you will return if root has split or not, okay? So generally speaking, you know, the algorithm will be able to do this until the point where you have propagated up to the point where the root node actually split into two. In that case, you need another algorithm. There's another function that has to handle that. So, you know, you will have to call insertion helper starting with root. If root has split, then create new root and point to the two new nodes. Okay, one is the old root, and the other one is the new node. Right, so you generally need two algorithms to be able to do that. But you know, the root splitting is a very rare event. And as I said, you would often keep these nodes not super full. And this is kind of happening because if your insertions are kind of semi-random, when you split, now both of the nodes are about half full, right? So basically you end up getting nodes that are empty enough that you will be able to insert lots of things. So that's the general idea of insertion. And there's some examples here. So let's say I inserted 57 here. Then it means that there was space. And then I inserted 65. 65 would go in here. But now I actually have to put a new node. And now I need to insert a key from here to here. So now this node actually has 4 keys. Okay. If I continue inserting, this node now has 5 pointers, which is the max that it can have. So that means if I were to insert to this one and this node has become full, I cannot point to that anymore from here, such as 90, in which case this node now is split into two. And now I had to insert one extra pointer up here. It's very painful to actually try to put these. It keeps trying to want to put them in, you know, not in the box. But I had 2 nodes here, but now I have 3 nodes. And it is possible that if you insert so much that the root may split, in that case you have a deeper tree. Okay? So this is the general idea of insertion. When a node becomes full, split, insert a pointer to it in the level above. The deletion goes in the reverse. So the deletion is very simple. Find the key value to be deleted, and if it exists, delete it, and update the parent node key value if necessary. Okay. So like for example, if I were to delete 78 from this node, then I need to change this key value to 84 so that it is, you know, more tight. But that's the main idea of deletion. So basically, before I go into deletion, let's just think about two simple things, and then I will go back to this one. Okay. Okay. Suppose I want to insert 57, right? So what would be the cost of doing that? Whenever I talk about cost, the cost is the number of disk pages that I read and write, right? So to first find where to store 57, I need to read this node, and this node. So I have to read 3 disk pages from disk into memory, right? So there's the cost of seek and read in them. Then I need to change this node That means for that information not to be lost, I need to eventually take this page from memory and store it back on disk, right? Otherwise, didn't happen, right? So that means 1, 2, 3 to read and 1 more to write because I want to store this. Of course, what happens is when you do have an overflow like this, now you have more information, right? So now you have read 1, 2, 3 to come here. And then this node has changed, this node has changed, and this node has changed. Now you have 3 disk pages to write. So the cost of a split is higher because you read more and you write more, right? So you don't want to continuously change your index structure considerably because we just saw it's actually very costly to read and write these pages. In addition, you are destroying my dream of, consecutive blocks, right? Because this one is probably not consecutive anymore, right? Unless you reorder or something. So, it is not great to be continuously changing. So the same thing is true for deletion, that when I'm deleting, I don't want a lot of change. So if I'm deleting, for example, this node and just 71, that means I have to read 1, 2, 3, and then just change this node and write it back. If I'm changing let's say 6 to 6, right? If I delete 6 to 6, I have to read 1, 2, 3, and I have to update this page and this page. So now I have 5 disk pages. Okay. So generally speaking, I don't want to be making big changes. So I want my structure to be semi-full and well-balanced. So when I did insertion, what I cared was that my nodes may become full, so I need to split. When I do deletion, what is the thing I care about? The nodes may become less than half full, right? If they are less than half full, then I'm wasting space. Okay? So that's the one thing I care. So if node is less than half full, okay? So what I'm going to do is I'm going to use an engineering approach. I'm going to try to fix it without trying too hard. Okay? So if it's less than half full, try to borrow a key value for leaf nodes or a pointer for internal nodes from a sibling. Okay. If possible, adjust key values and done. Okay. So let's see an example here. So let's say this. If I delete 30 from this one, what will happen is that now this is less than half full. I have less than 2 things. So what I will try to do is borrow from left or right siblings. Okay? You will actually not borrow from this one because it's from a different node. So you would want to borrow from a sibling that has the same parent, right? Because otherwise I will have to go back and read and update this. So generally you would want to borrow from a sibling from the same parent, but that's actually easy because you have 400 siblings. Well, you only have left and a right, but that's very likely that you will have a left and a right in a family of 400. Okay, so that means if I can borrow from here, then I will be good, and I can because this has more than 2. So I'm going to borrow it. Since I borrowed 17, I need to adjust this. Then I'm done. Okay, so that's the first thing I try to do. I can borrow from both neighbors as long as they have the same parent. If possible, that's my option. Okay. then of course I am obsessive. So let's say I keep deleting. Now I delete 7 from this one. I try to borrow from this neighbor, but I no longer can. So now both me and my sibling are very empty. In that case, I'm clearly wasting space. So what I will do is I will merge with my sibling. So then I will merge these 2 nodes into a single node. That means one of them is going to be deleted. So then I'm going to delete one of these pointers, and I'm going to delete one from the parent. So now, when I'm done, I'm going to look and see if this node is sufficiently empty or not. Okay? Now this node has only 2 pointers, which is still okay, because I want to have at least 2. But if I were to keep deleting from this, then this node is going to become less than empty. If this node is less than empty, then I will try to borrow from its sibling, right? So this node and this node. Okay, so now let's say I merge this, and now this node has only 1, and it tries to borrow from this node. It cannot, because that also only has 2. So in that case, what will happen? So then I will merge with this node, in which case the root is no longer necessary because I don't even have 2. Then I will delete the root. So in this case, my tree shrinks because I only have 1 level, right? So the deletion can cause, very rarely, for the tree to shrink. So this is the general idea of deletion. If it is possible to borrow a key value from the sibling, borrow and adjust. Else, I need to merge with one of the siblings and delete a pointer from the parent recursively. Okay. So I will keep repeating this by basically repeating the same delete property from the parent. And in the same way, the deletion basically will have call deletion helper from root if root now points to a single node in the next level, delete root and make the next node the new root. Okay? So in the same way, you have to call it from a helper to see what happened. If it turns out that you actually deleted everything, then you have to change the root. Okay? So like when AI has become self-aware, then they can solve this problem with a single function. But currently, it is not possible. Okay? So, any questions about this? This is kind of an engineering idea. I am trying to keep my nodes roughly more than half full. So I do 2 things, not exact opposite of each other. If I did exact opposite of each other, they will cancel each other out. So if I borrowed from neighbors inserting and then also in deletion, they will kind of cancel each other out. So I do slightly different things. I split on insert and I borrow on delete. And this way they kind of create generally a good outcome. So let's see kind of a simple example of how good B trees are. So let's say I'm going to create a B tree for actors in my database. Now I don't have the full actor database, but let's say that I have about 4 million actors. because the one I gave you is a very small snapshot. So in fact, if I have 4 million actors, probably I have 400,000 movie role, thing. But let's say I have 4 million actors, okay? So I want to create an index on actors, actor ID. And let's say that a disk page is about 4K. And in each page, I am going to store the ID value and a tuple pointer. Let's say this is roughly about 10 bytes per tuple. Okay. So the disk page is about 4K. Some of that is taken by header. So let's say, 72 bytes of header and 4,000 bytes of free space. So that means each page stores about 400 key values and pointers. Okay. Now, in this case, there's +1, -1 because, we are going to disregard that. That's small potatoes. So in each disk page, I can store about 400 tuples, basically. That's all it says, right? So let's figure out how big this index is going to be for this specific one. So I have 4 million actors, so 4 times 10 to the 6. And I can store about 400 tuples per node, right? So tuples per node. That would mean how many leaf nodes? So 4 times 4, 10 to the 4, right? 10 to the 4 leaf nodes. Now you have to correct me if I make a mistake here. So which is about 10,000. So that means I will have 10,000 leaf nodes that point to the tuples in my database. So now on the upper levels, I need to index these leaf nodes. So in the level above, I need to address 10,000 leaf nodes. Okay. So, and again, I can store up to 400 in a single page. So 10,000 divided by 400, so get rid of this, and which is what, 25? 25 nodes in the next level. Okay, so to address 10,000 leaf nodes, I need basically 25 nodes in the next level. And then to address those 25 nodes, how many nodes do I need above? One, right? Because one node can index up to 400. I only have to index just 25, so I only need one root node, right? So this is my tree. So this is my tree is 1 root, 25 next level. Then I have 10,000 leaf levels. Which addresses 4 million tuples. Now, if you actually do this over and over and over, you will find that as this grows very, very quickly, this grows very slowly. In fact, this grows logarithmic, obviously, right? But is the logarithmic base 2? Logarithmic base n, right? Because at each point I divide it by a factor of n, right? I need x divided by n. So basically, I need number of levels is in the order of number of tuples in relation log base n of this. Right. So basically, B-trees have these very interesting and useful points. You can use them for many different types of queries. They grow very slowly, even though your data is huge. And they are optimized, for a magnetic disk. So your performance is probably even better than what this tells you because of being able to do sequential scans at the leaf level. So because of that, you will see a lot of indices that are variants of B-tree. So on Thursday, I'm going to talk to you about one variance that's used for spatial data. Then we are going to talk about two separate index types. One is hashing, less used but still valuable. And one is a bitmap, which is very, very important these days, and I'll tell you why. And then we will move on to talking about how to use these in query processing as well as other algorithms for query processing. And wait for the homework at the end of today.